Impossible places. The secret history of our planet. "40-million-year-old whale skeletons with hind limbs lie in Egypt's desert. A dam revealed Iceland's canyon. These contradictions expose how impossible landscapes formed and what now holds them together. These places are often reduced to impossible sights. I see something more demanding. Rock bent by pressure, ice cutting valleys, water laying mineral terraces, and settlements built where heat, cliffs, or scarcity leave little room for error. Their strange forms are records, but spectacle can bury the evidence. And some of it is being altered now by retreating ice, diverted rivers, extraction, and rising seas. In this video, we read the evidence inside these landscapes to uncover the forces that made them and the human work that keeps life possible there. Hundreds of ancient whales are preserved in a desert that was once a warm sea. Around 40 million years ago, the Tethys Sea covered Wadi Al-Hitan, now dry ground about 150 kilometers southwest of Cairo. The sandstone and shale hold hundreds of early whale fossils, many preserved as connected skeletons rather than bones scattered by currents. Sediment repeatedly sealed the bones into the shallow seafloor before currents could pull them apart. Fast cover preserved the evidence. Basilosaurus could exceed 15 meters, yet its marine body still carried tiny hind limbs that could no longer bear weight on land. Smaller Dorudon had the streamlined body and reduced rear limbs of a fully aquatic whale. Together, these skeletons record a decisive stage in whale evolution. Sharks, rays, turtles, crocodilians, shells, and mangrove roots rebuild the coastal habitat around them. This desert once carried an entire food web. Wind now strips the old seabed and returns vertebrae and ribs to daylight. The same erosion that reveals the record also leaves it exposed. Wadi Al-Hitan is not empty ground. It is an ancient seabed still carrying the physical record of whales leaving land behind. A canyon built by lava remained hidden until engineers pulled most of its river away. Once a hydropower diversion cut the flow, walls of 5- and 6-sided basalt prisms, some nearly 30 meters high, rose into view. Studlagel's geometry began millions of years earlier, when a thick body of basaltic lava cooled and contracted. Cracks spread at roughly even angles. The result was ranks of stone columns that resemble cut masonry, though no builder set them. Volcanic cooling did all the work. For centuries, the Yokulsa Ardal drove through the gorge with glacial sediment and heavy force. Its depth concealed most of the volcanic structure. Then, the Karanjukar hydropower works redirected most of that flow into the Halslon Reservoir and onward to the Fliotsdalur power station. Engineering did not make the canyon. It lowered the river that had kept the canyon out of sight. At low flow, clearer water can turn blue-green. Summer melt, Heavy rain or reservoir releases can quickly restore a darker, stronger current. That change also governs access. Steep paths, slippery columns, falling rock, and sudden water shifts keep this exposed terrain difficult. Studligil is therefore not untouched nature. It is a volcanic record open to wider view when human engineering rewrote the river. Niagara Falls looks fixed on the border, but its crest has been crawling upstream for 12,000 years. At Horseshoe Falls, most of the river crosses a curved crest more than 750 meters wide, while two smaller falls divide the remaining force. The falls began when retreating ice sheets reorganized the Great Lakes and sent water across the Niagara escarpment. That rerouting created a moving edge, not a permanent monument. Below the surface, a hard cap of dolostone rests on softer shale. Water strips the shale from beneath, leaving the upper rock unsupported. Freeze and thaw widen the damage. Large slabs eventually give way, and the new lip begins the same work farther upstream. Before engineers tightened control, that repeated undercutting could shift the crest by roughly 30 centimeters or more in a year. Now, reinforced banks, hydroelectric diversions, and an international control structure hold back much of that movement. Engineering has slowed geology without stopping it. A treaty signed in 1950 makes the spectacle a negotiation. The United States and Canada maintain minimum daytime flows, then divert more water to power stations at other hours. Niagara's record lies beneath the spray. Ice redirected the river, erosion moved the cliff, and engineering now controls the rate. More than 1.5 million wildebeest move across these plains, yet the force directing them is often invisible. Their annual circuit covers roughly 800 kilometers, following shifting rain, fresh grass, and surface water across Tanzania and into Kenya. The park spans nearly 15,000 square kilometers, but its borders hold only part of this larger ecosystem. Early year rain gathers herds on southern plains, where mineral-rich volcanic soil grows nutritious grass. Hundreds of thousands of calves arrive within one compressed season. Then the ground dries. The herds turn west and north, spending strength against distance, scarce water, river crossings, disease, and predators. This is not a parade running on a fixed schedule. Rain changes the route each year, making flexibility the real engine of survival. The migration also rebuilds what it consumes. Grazing cuts old grass, while dung and organic remains return nutrients that help keep the plains open. Maasai communities retain deep pastoral and cultural ties to the wider region, though park boundaries and conservation rules have restricted access to former grazing land. The Serengeti lasts only while rain corridors stay open and coexistence reaches beyond the park. Its abundance is not a fixed inheritance. Water, soil, animals, and people must keep remaking it. Beneath Venice's stone, dense ranks of timber driven into lagoon mud still carry the city. Venice occupies more than 100 low islands in a shallow Adriatic lagoon, linked by over 400 bridges and canals used as streets. After the Western Roman Empire declined, refugees expanded settlements where firm ground was scarce. Building here meant forcing stability into waterlogged sediment. Workers drove dense clusters of wooden piles into the mud, then capped them with timber platforms and stone foundations. Low oxygen slowed decay, keeping the buried structure firm. The lagoon became both moat and maritime highway. Trade with Byzantine and Islamic ports left its record in arches, mosaics, warehouses, and waterfront palaces. That old bargain with water now grows harder. Subsidence, rising seas, storm surges, and the Sirocco wind push exceptional tides deeper into brick and stone. Salt does not need a dramatic flood to work. It enters walls, weakens masonry, and turns routine maintenance into a permanent engineering campaign. At the lagoon's 3 inlets, the Meuse barriers can rise against exceptional tides. More frequent closures, however, can disrupt shipping and alter lagoon ecology. Fewer than 50,000 residents remain in the historic center, and that loss threatens the workforce, keeping this hydraulic structure alive. Venice survives not by romance, but by continuous labor against the sea. The stripes that made this mountain famous are ancient, but less persistent snow is leaving them exposed for longer. Vinicunca stands about 5,000 meters high, where ancient sediment beds were compressed, folded, tilted, and lifted into thin air. Mineral chemistry drives the color. Iron-bearing layers produce reds and browns. Clays and altered minerals create green, yellow, and cream bands. Weathering exposed sharper boundaries between the beds. Seasonal snow still covers the stripes, so the slope can disappear again beneath white. The rock is ancient, but its global fame is new. Photographs spread around 2015 as road access shortened the approach. Warming did not create the stripes, and claims that a glacier hid the entire mountain until recently lack firm evidence. The stronger climate signal is ice loss, measured across neighboring Andean ranges. As snow persists for less time, high slopes remain exposed longer while nearby glaciers continue to shrink. Popularity adds another pressure. Local pastoral communities now share the cold plateau with heavy foot traffic, vehicles, and trail erosion. Vinicunca holds 2 records: mineral beds raised with the Andes and modern ice loss nearby. Ancient rock and present climate are visible on one slope. The red walls of Abyaneh hold an archive absent from Standard Persian, a living archaic dialect. At roughly 2,100 meters beneath the Caucasus Mountains, centuries of isolation helped that speech, and the settlement around it resist wider cultural change. Its central Iranian dialect carries vocabulary, sounds, and grammar lost from Standard Persian. These features link it to Middle Persian and Iran's pre-Islamic past, not to Sassanid speech preserved unchanged. Iron-rich earth gives the mud brick its red color. Timber braces the houses against movement, wind, and hard mountain weather. Buildings climb in tight tiers. One roof becomes the path or courtyard of the home above, extracting usable ground from a steep slope. Narrow lanes block hard wind and summer sun. Small openings hold warmth when mountain temperatures fall. Patterned head coverings and full skirts still appear during ceremonies and busy seasons. Yet this continuity now carries pressure. Education and work pull residents toward larger cities. The permanent population is far smaller than the house count suggests, then expands when families return for holidays. Abbiane matters not as a village frozen in antiquity, but as a vulnerable record still being spoken. Its history survives only when daily life keeps those old sounds in use. The Alps' longest glacier preserves climate evidence, while its own ice retreats. Aletsch runs for more than 20 kilometers, yet since around 1870, its front has retreated by more than 3 kilometers. Its scale begins at Concordia Platz, where 3 tributary ice streams converge. In places, their joined mass exceeds 800 meters in thickness. Gravity drags that mass downhill, slowly deforming it. Dark parallel bands are medial moraines, debris gathered where tributary edges meet and carried through the Alps. Snow compresses into firn, then ice, trapping particles and seasonal signals. But this is no neat stack of untouched pages. The glacier moves and deforms. Its clearest diary lies along the margins. Paintings, photographs, survey markers, and measurements since the 19th century show where the ice once pressed against the valley. As the surface drops, bare rock emerges, and slopes above the former ice become unstable. The landscape records both retreat and the physical stress it leaves behind. Faster melting can raise runoff at first. Continued loss, however, weakens the glacier's ability to release water through dry summers, shifting pressure far beyond the ice. Aletsch is therefore more than stored climate evidence. It is a climate diary whose most decisive entry is the archive shrinking in full view. A desert oasis in Peru now survives partly because water is pumped into its lagoon. Rain near Ica is too scarce to sustain the lagoon, and the underground reserve that once fed it naturally is being drawn down by agriculture. Huacachina occupies a small depression on Peru's exceptionally dry Pacific coastal plain. High mobile dunes enclose water, palms, buildings, and work. Local legend says a young woman or princess formed the lake from her mirror. Belief in healing water helped make it a wealthy Peruvian resort in the early 20th century. The physical record is harder. The lagoon depended on a regional aquifer because surface rainfall could never replace what heat and use removed. Then irrigated vineyards and water-intensive crops expanded around Ica. Wells pulled from the same reserve, lowering the water table and reducing the oasis's natural inflow. Authorities have periodically added pumped water to stabilize the lagoon. What appears to be a natural refuge is now also a piece of groundwater engineering. Tourism adds another load. Hotels, dune buggies, and sandboarding generate income around a tiny basin, but also bring noise, shoreline pressure, waste, and erosion. Huacachina endures where legend, farming, tourism, and engineering all meet. Its water now records a blunt fact: even an oasis can be overdrawn from below. A hydroelectric reservoir has turned invisible decay into white disks locked inside winter ice. Built on Alberta's North Saskatchewan River in the early 1970s, Abraham Lake floods soil and vegetation behind the Bighorn Dam. That submerged material does not become inert. Microbes working in oxygen-poor sediment break down plant matter and release methane. The gas rises in bubbles. When the surface seals, each new freeze traps another layer beneath the last, building vertical stacks of pale disks. Wind strips snow from the exposed reservoir, leaving unusually clear ice and a direct view of activity below. What looks decorative is a biological record still being written. The engineered lake may intensify that record. Flooded soils and plants can feed decomposition with material that a natural lake would not receive in the same way. The dam also keeps the surface from behaving like fixed ground. Water levels shift with operations and electricity demand, opening cracks, pressure ridges, hidden voids, and patches of weak ice. Summer exposes another force: fine glacial sediment, ground from mountain rock and carried into the reservoir, scatters light and turns the water blue-green. The frozen disks are not ornaments. They are visible proof that flooded life keeps changing an engineered lake from below. Cappadocia's most consequential architecture is not the stone towers above, but the inhabited depth concealed beneath them. Millions of years ago, eruptions spread thick ash across central Anatolia. It hardened into soft, tough stone, firm enough to stand yet workable enough to excavate. Water, wind, and repeated freezing removed weaker layers. Harder caps protected fragments below, leaving cones, ridges, and the formations known as fairy chimneys. But erosion only prepared the material. People turned the same rock into houses, storerooms, pigeon lofts, monasteries, and frescoed churches. The deeper record lies in complexes such as Derinkuyu and Keimaklu. Narrow passages connect many levels, while ventilation wells pull air far below the plateau. Storage chambers, kitchens, water access, animal spaces, and heavy rolling stone doors allowed communities to remain below during raids and political upheaval. These were not comfortable modern cities. They were organized refugees and working spaces expanded over generations. Their first builders and earliest dates remain debated, but Byzantine Christian communities used many chambers heavily during unstable periods. The decisive fact lies in the method. Almost nothing had to be carried in. Removing stone created shelter, storage, defense, and airways inside one continuous mass. The towers record erosion. The underground chambers record how human pressure turned the same volcanic stone into refuge. Rain still cuts apart a summit nearly 3,000 meters high, built from sandstone almost 2 billion years old. Where Venezuela, Guyana, and Brazil meet, Mount Roraima is ringed by cliffs hundreds of meters high. These walls, are remnants. Ancient Roraima group sandstone endured while surrounding material was stripped away, leaving a table of rock above the lowlands. Rain continues the excavation. It enters joints, widens fissures, cuts gullies and caves, feeds dark pools, then drops from the rim in waterfalls broken by wind. Above the cliffs, cold, wet, acidic ground holds little food for plants. Compact growth and water-holding structures conserve resources. Some species trap insects to gain scarce nitrogen. Long separation from the lowlands has produced plants and small animals found nowhere else. But this is not a sealed world. Spores, insects, and birds still cross the cliffs. That balance matters more than the fantasy of a sealed lost world, although Roraima helped shape Arthur Conan Doyle's novel. Isolation slowed exchange, it never stopped it. Summit soils recover slowly from trampling, making guided routes and waste control essential. Roraima is a time capsule still open to rain, rare arrivals, and human pressure. This famous avenue is not a surviving wilderness, but the exposed frame of a forest that people cleared away. Along an unpaved section of Route 8 near Morondava, centuries-old Grandidier's baobabs now stand apart where many other trees and understory plants once grew. Their huge cylindrical trunks store water through the dry season. People often spared them because they were useful, culturally important, difficult to cut, or marked property and paths. Around them, generations cleared land for rice, grazing, fuel, and settlement. The remaining trunks reveal how much was removed, not how much forest survives. What matters here is what no longer stands. An isolated giant may look untouched, yet its isolation is the evidence. Temporary protected status in 2007 brought greater attention, but guarding mature trunks cannot rebuild the dry forest beneath them. Fire, livestock, compacted soil, altered drainage, and poor seedling survival block regeneration. Protecting old trees alone preserves a lineup, not a forest. Residents still work and cross the farmland around the trees. Conservation must therefore manage water and livelihoods, rather than turn the avenue into an empty exhibit. The avenue carries real weight only when each trunk is read as living evidence. Water stored inside, forest cleared outside, and recovery now tied to the people working the land. One of Europe's most voluminous glaciers is also a lid over active volcanoes. Vatnajökull covers a vast part of southeastern Iceland, while Grímsvötn below it ranks among the country's most frequently erupting volcanoes. Heat rises into the glacier from below. Meltwater gathers in depressions until pressure opens a route under the ice. Then the hidden water escapes as a jökullhlaup, driving sediment, ice blocks, and volcanic debris across the outwash plains. Roads and bridges can face the force, far from the eruption. The glacier does not merely cover this activity. Ash-rich layers remain embedded in the ice, then bend and travel as the ice flows. At the margins, summer meltwater enters fractures and cuts new channels. Some widen into blue caves, where dense ice absorbs more red light. The color looks permanent. The structure is not. Flow, melt, and collapse rebuild the drainage network each year, so winter access depends on fresh surveys and local guides. Protection here cannot stop at the ice cap. Vatnajökull National Park also holds the volcanoes, flood routes, outlet glaciers, and plains, shaped by what happens underneath. Vatnajökull is one body, not two opposing landscapes. Its ice records the heat below, and every flood route proves the cold surface can never seal the land. A medieval sea power built towns and farms on cliffs that barely offered room for a road. Between the 9th and 11th centuries, Amalfi's merchants connected Mediterranean ports, while settlements climbed narrow ledges above small harbors. The limestone coast drops into the Tyrrhenian Sea. Geography forced houses, churches, lanes, and stairways to stack upward because level ground was scarce. Dry stone walls hold thousands of agricultural terraces. They slow runoff, retain soil, and make plots for vines, olives, and the long sfusato amalfitano lemon. That ground is not finished infrastructure. Many plots still demand hand labor because steps, footpaths, and small transport systems reach where ordinary machinery cannot. Before the coastal road, boats and mule tracks linked communities more reliably than routes across the cliffs. The Maritime Republic was shaped by that fact. Its merchants looked outward because the land resisted easy movement. The maritime code associated with Amalfi remained influential even after the Republic's political decline. The same slopes still demand repair. Heavy rain can loosen rock and ground, while abandoned terraces lose support. Tourism presses roads, water supplies, and housing. Medieval power survives here as maintenance. Every repaired wall, harbor step, and worked ledge keeps the cliffs habitable under modern pressure. The train curves through open air, climbs above the gorge, then disappears straight into a vertical alpine cliff. Completed in 1902, the Landwasser Viaduct carries one track about 65 meters above the river on 6 masonry arches. The gorge offered almost no room for a conventional approach. Each arch spans about 20 meters, yet the entire bridge bends on a radius of roughly 100 meters, while the rails continue uphill. At the far end, the final arch meets rock and sends the train directly into the Landwasser tunnel. That decision removed the need for a broad embankment or a station on unstable ground. Across the albular line, tunnels, tight curves, and spiral sections gain altitude without demanding gradients the trains could not grip. Now part of a UNESCO-listed railway landscape, the bridge is one hard answer within that larger alpine route. Builders used local stone, and cranes climbed with the rising piers. That reduced the need for full-height timber scaffolding across the gorge. Every visible choice records resistance from rock, slope, altitude, and turning radius. Its survival is less static. Water, freeze-thaw, and exposed masonry still demand inspection and repair above the gorge. Uyuni's white expanse is the concentrated residue of ancient lakes that had no outlet. Salar de Uyuni covers more than 10,000 square kilometers of Bolivia's Altiplano, roughly 3,650 meters above sea level. In wetter prehistoric periods, large lakes filled this closed basin. As the climate shifted, evaporation removed the water and concentrated its dissolved minerals. Salt, clay, and volcanic sediment settled in alternating layers. The white crust is therefore a physical archive, built by repeated cycles of flooding and retreat. During the dry season, evaporation draws brine upward. Contraction and mineral growth split the surface into repeating polygons. Rain reverses the effect. A shallow film spreads across the exceptional flatness, turning the ground into a vast reflector without restoring the vanished lake. Even Incahuasi records the earlier water. Ancient reef-like carbonate material now rises above the salt, carrying giant cacti. Lithium lies dissolved in brine, not as ready-made metal. Recovery requires pumping, concentration, chemical treatment, and separation from other salts. Development can strain freshwater supplies, alter brine movement, and test whether indigenous communities share the gains. Uyuni records both eras, vanished lakes in its crust, and lithium brine sought for future batteries below. One desert crater proved what geology once resisted. Objects from space can remake the ground. About 50,000 years ago, an iron-nickel body tens of meters wide crossed the atmosphere at several kilometers per second and collided with the plateau. The collision excavated a cavity nearly 1.2 kilometers wide and about 170 meters deep. Rock layers were driven outward, and some along the rim flipped over. Fragments classified as the Canyon Diablo meteorite were recovered around it. Its origin remained disputed, with volcanic activity as the rival explanation. In the early 20th century, mining engineer Daniel Barringer argued for a cosmic collision. Expecting a large buried meteorite, he spent years drilling without finding it. That failure exposed a mistaken assumption. Much of the body had fragmented, melted, or become vapor, leaving no giant core to recover. Later, geologist Eugene Shoemaker identified pressure features and showed that the structure matched impact mechanics, not a volcanic event. The disturbed rock held the proof. It became the first terrestrial crater widely accepted on decisive geological evidence as an impact site. Apollo astronauts later trained here to recognize breccias, ejecta, and disturbed strata before lunar missions. Its overturned rock preserves the decisive finding: cosmic collision, not volcanism. A ceiling of blue-green lights is actually a field of feeding traps. Each glowworm larva lowers multiple sticky silk threads, using its own light to draw insects out of the underground air and stream. Rainwater starts the larger story above ground. After absorbing carbon dioxide from soil, it turns mildly acidic and works into limestone joints, slowly cutting passages, shafts, and underground streams. That stone architecture then creates the conditions the larvae need: damp ceilings, stable humidity, moving air, and water that keeps delivering small insects. If the silk dries, the trap fails. The glow is not decoration, and that distinction changes the cave completely. Light here is bait, while darkness gives the signal its power. The colony is sensitive to shifts that are almost invisible from outside. Temperature, airflow, carbon dioxide, and flooding can all change its activity. Maori communities knew these caves before Chief Tain Tinarau and English surveyor Fred Mace documented their exploration in 1887. Tinarau later guided early visitors, and his descendants remain part of the cave's history and management. Today, quiet boat traffic, visitor numbers, and artificial light are controlled because the colony survives only within a narrow range of darkness, airflow, humidity, and stream life. Glaciers cut a rock basin nearly 1,000 meters deep, where Aurlandsfjord now reaches 30 kilometers inland. It narrows to under 2 kilometers, while the basin drops far below present sea level. During repeated Ice Age advances, glaciers forced rock fragments across the bed. The debris ground, widened, and deepened the valley into the U-shaped trench that still controls movement through it. When the ice retreated, seawater occupied the overcut basin. Smaller glaciers had cut less deeply, leaving hanging valleys whose streams now descend from mountain walls, rising more than 1,800 meters. That geometry is evidence, not scenery. The vanished glacier still dictates where water falls, where boats pass, and where level ground can hold a farm or settlement. For centuries, the fjord offered an easier corridor for people and goods than the mountains above. Farms and villages took hold on narrow deltas and ledges because the ice had left little usable land. Flom became a junction for mountain rail and road tunnels, driving steel through terrain the glacier still controls. Cruise traffic brings jobs, emissions, and crowds into the same confined trench. The Ice Age shape still directs modern movement and pressure. What looks like a stone forest began as a seabed. Its limestone formed from marine sediment about 200 million years ago, then rose, fractured, and exposed its cracks to rainwater. That rain absorbed carbon dioxide from soil and became weakly acidic. Drop by drop, it widened the fractures into deep slots, caves, underground drains, and blade-like pinnacles. The name Singi is commonly understood as ground where bare feet cannot pass. It fits. These edges make ordinary movement difficult, even across short distances. This is not a crowd of separate spikes. It is the remaining framework of one limestone mass, opened from above and within as water carried dissolved rock away. The cuts also divide life into tight ecological pockets. Dry, exposed crests sit close to shaded canyons that hold moisture, giving lemurs, reptiles, bats, and endemic birds sharply different refuges. Rivers and mangroves add more barriers around the plateau. Researchers and visitors cross selected sections with ladders, cables, suspension bridges, and narrow paths. Much of the strict reserve remains inaccessible. Even access follows the water. Rainy season roads can become impassable for months, while rain keeps cutting the 200-million-year-old seabed into sharper stone. Mineral water whitens Pamukkale one fragile film at a time. When the flow shifts, the mountainside darkens. The terraces climb roughly 160 meters above the Büyük Menderes Valley, carrying thousands of years of mineral deposits. Underground, thermal groundwater moves through limestone and absorbs calcium carbonate. At the surface, pressure falls, carbon dioxide escapes, and calcite grips channels and pool rims. Each film is fragile. Repeated flow thickens it into travertine shelves, while a dry channel can discolor before another turns white. Above them, Hierapolis grew into a Hellenistic and later Roman spa city. Baths, temples, and a theater show that geothermal water shaped health, worship, and urban life. That bond also brought pressure. In the 20th century, hotels, roads, footwear, and unrestricted bathing damaged and dirtied the young stone. The hotels were removed. Water is now routed through controlled sectors, and access is confined to designated barefoot paths, so every terrace cannot remain flooded at once. One limited flow built the white slope and drew Hierapolis to its rim. Because fresh travertine depends on continued deposition, every diversion decides which terraces brighten and which darken. The doors that made Makunic famous are too low for most adults, but they prove less than the legend claims. Near Iran's border with Afghanistan, old houses sit partly below ground, with narrow entrances, low ceilings, and compact rooms shaped by severe scarcity. Earth, stone, and scarce timber had to do maximum work. Smaller rooms needed fewer materials, shed less heat in winter, and were easier for a household to warm. That practical design became folklore about exceptionally short people, later marketed as the village of Lilliputians. Low doors alone cannot establish who built them or how tall the builders stood. Historical nutrition and isolation may have affected average stature, yet dates for the settlement vary, and repaired earthen walls cannot settle who first built them or exactly when. Life depended on scarce water, small plots, livestock, and hardy crops suited to the arid ground. Every wall and harvest carried the same constraint: use little, retain heat, waste no water. Roads, modern housing, education, and employment pulled daily life away from many older dwellings. Rain, wind, and neglected maintenance now strip earthen walls that require regular repair. The low doorway preserves a harder truth. Scarcity dictated the house, while missing evidence leaves the builder's full history unresolved. Over thousands of years, modest Oaxacan springs have built a stone waterfall nearly 30 meters down the cliff. At Hirve el Agua, modest carbonate-rich springs have laid mineral over the cliff for thousands of years, creating the pale Cascada Grande. The name means the water boils, but the springs are not boiling hot. Escaping gas makes them bubble at the surface, creating the illusion of heat. As the water spreads, pressure drops and carbon dioxide escapes. Calcium carbonate then grips the slope, repeating the deposit until two pale travertine masses cover the cliff. The springs also supported a network of channels associated with ancient Zapotec communities. Those cuts redirected limited water across dry ground, turning geology into food production. Long before tourism, the decisive achievement was control, holding, dividing, and carrying a modest flow through dry mountain terrain. That tension has not vanished. Flow is modest. Surrounding communities face water scarcity, and disputes over access, tourism revenue, and maintenance have brought periodic closures. Here, the cliff and the canals preserve one shared record. Mineral water built the stone, and Zapotec engineers forced the same scarce flow toward dry plots. Warm water reefs formed the rock that now stands more than 3,000 meters above the sea. The Dolomites began over 250 million years ago when warm tropical water covered this part of northeastern Italy. Marine organisms and lime-rich sediment built reefs and broad carbonate platforms around volcanic islands. Burial and chemical change later turned portions of that limestone into dolostone. Then the African and European plates pressed together. The former seabed folded, fractured, and rose with the Alps, converting ocean deposits into pale walls and pinnacles. The uplift did not finish the work. Glaciers cut broad valleys. Water widened cracks. Repeated freezing and thawing pried loose more rock. Rockfall still strips material from the towers and feeds the scree below. Their sharp outlines are temporary stages of erosion, not permanent architecture. The same stone that records vanished seas also directed human movement. Mountain passes carried trade and herds, then military routes and trenches during the First World War. At low sunlight, the carbonate faces can turn pink and orange in the effect called enrosadera. The color is striking, but the structure beneath carries the real weight. Marine life built these peaks, continental force lifted them, and ice cut them. Rockfall now continues the transformation, returning a fossil sea to rubble in open air. Each breeding season, lesser flamingos gather in water caustic enough to exclude most large animals. Parts of Lake Natron reach a pH of roughly 10.5, yet it remains one of East Africa's few regular breeding grounds for lesser flamingos. Its chemistry begins in a closed East African rift basin beside Oldoinho Lengai. Runoff and springs bring volcanic minerals, but no river carries them to the sea. Water escapes largely by evaporation. Salts stay behind, concentrating as the dry season contracts the lake into crusted flats and shallow brine pools. Pigmented microorganisms tolerate the brine and turn parts of the lake red or orange. They also feed lesser flamingos, tying volcanic rock to a living colony through a short food chain. When depth and salinity align, Flamingos build mud nests on isolated flats. Caustic water discourages many mammalian predators, while specialized legs and feeding anatomy let the birds exploit what excludes others. Protection can reverse quickly. Floodwater can cover nests. Severe drought can open dry access across the flats, exposing colonies that isolation once guarded. The lake persists by remaining chemically extreme, yet breeding depends on a narrow balance of water and salt. Natron's harshness is the barrier that gives flamingos room. Families once returned each winter to rooms cut directly into a mountain in southeastern Iran. In 2015, UNESCO listed a cultural landscape where homes, storage rooms, animal spaces, and communal chambers were excavated through soft volcanic rock. The dwellings are known as quiche. Low rooms sit behind recessed entrances, with thick stone doing work that freestanding walls would struggle to match. During severe summer heat, rock stays cooler than exposed buildings. In winter, the same mass holds warmth, reducing the force of a climate that punishes light construction. But these chambers were never the whole settlement. Families historically moved with livestock and farm work between winter rock houses, spring pastoral shelters, and summer quarters near gardens and fields. The blackened ceilings carry a harder record than uncertain claims about the village's earliest date. Generations of indoor fires marked the same stone, while residents repeatedly enlarged and adapted the rooms. Today, migration toward cities and declining seasonal pastoral work threaten the knowledge needed to maintain this landscape. Empty chambers alone cannot preserve the timing of herds, fields, repairs, and seasonal movement. Meyman's achievement is direct. People used the mountain's mass to endure heat, cold, and seasonal movement. When families stop moving, repairing and returning, the architecture remains, but the adaptation disappears. At the equator, cold water helps penguins survive, while volcanic ground keeps building beneath them. Nearly 1,000 kilometers west of mainland Ecuador, the Nazca Plate moves across a mantle hotspot, making younger, more active islands in the west and older, worn islands in the east. Isolation does not freeze life, it forces life down separate paths. The few species that crossed the Pacific met different food, climates, and rivals on each island. Marine iguanas evolved to feed on algae in cold water. Giant tortoise populations developed different shells and feeding strategies as distance cut one island off from another. That variation caught Darwin's attention in 1835, especially among mockingbirds and tortoises. The famous finches became central evidence only after their specimens were studied and classified more carefully. The laboratory also depends on moving water. The cool Humboldt Current, the nutrient-rich equatorial undercurrent, and warmer tropical flows meet here, feeding seabirds, sea lions, penguins, and marine food webs. But the mechanism is exposed. During El Niño, weakened upwelling can sharply reduce food in the sea, while goats, rats, insects, and invasive plants disrupt life on land. Quarantine, eradication, and limits on settlement protect evolution while it is still happening. This is a living record. Rock, Current and isolation are still shaping life. Wind, salt, heat, and rare rain carve white towers from the floor of a vanished Cretaceous sea. North of Farafra Oasis, the chalk accumulated from calcium-rich remains of microscopic organisms and fine sediment settling through a warm sea. Later, uplift exposed those beds inside the Farafra Depression. Aridity did not preserve them intact. It handed the old seabed to a new set of forces. Wind-driven sand cuts the soft chalk, but wind is only part of the work. Salt crystals expand, daily heating strains the rock, and rare rain loosens weak surfaces. Different layers resist at different rates. Softer chalk retreats beneath harder caps, producing mushroom profiles, while fractures steer the growth of towers and ridges. These forms are temporary, not finished monuments. Narrow stems keep thinning, and some eventually give way, breaking more chalk into loose sediment. The human foothold lies nearby. Groundwater and springs support Farafra Oasis, a settlement and stopping point in a region where surface water is scarce. Protection began in 2002, but access brings its own pressure. Camping and four-wheel drive traffic create income while tires, litter, and accidental contact damage fragile chalk. The White Desert is marine history, exposed by uplift and still being dismantled by desert weather. On a coast pressed by summer heat and humidity, Laft's tallest structures work as engines for moving air. The settlement has lasted more than 2,000 years beside the Strait of Hormuz, despite scarce freshwater and punishing summers. Internal veins divide each Bagia. Openings catch useful winds, pressure drives air into rooms, and warmer interior air escapes through another face of the shaft. Thick earthen walls, shaded courtyards, small openings, and connected rooms slow heat gain while the towers keep air moving. In humid coastal air, their main value is ventilation, not the strong evaporative cooling possible in dry inland cities. Water required separate engineering. Domed cisterns stored brief rains, while the rock-cut golden wells captured runoff, filtered through surrounding ground. Tradition assigns one well to each day of the year, though totals vary. The principle is firm. No burst of rain could be wasted. Fishing, dhow traffic, pearling and trade also shaped the town. Nearby Hara mangroves along the coast shelter working boats and provide nursery habitat for marine life. Together, towers, wells, lanes, and waterfront form one defense against heat and water scarcity. Their continued use makes the larger pattern plain. Endurance is active adaptation, not stillness. I take one lesson from these places. Spectacle is the surface, evidence is the substance. A cliff can preserve an ocean. A salt flat can hold the raw material of a new industrial age. A village can encode centuries of answers to heat, drought, and unstable ground. But no record is secure. Ice thins. Water is redirected. Coastlines face greater pressure. Extraction can turn an ancient basin into strategic ground almost overnight. Reading landscapes this way changes what protection means. It is not enough to preserve a view. The forces, habitats, water sources, and human knowledge that hold the place together must also endure. These sites are not scenery outside history. They are active evidence of planetary change and of the power this age now holds to erase or extend that record. Follow this series as it looks past spectacle and tests every impossible place against rock, water, climate, and human endurance. The deeper record is where wonder gains its true weight.